In this lesson, we're going to take an initial look at stereochemistry, focusing on EZ and cis-trans isomerism. Stereochemistry is really just the study of stereoisomers. Stereoisomers are isomers that differ only in the spatial arrangement of atoms and that are not interconvertible by free rotation. So here I have a pair of models. These are models of ethane, and these are not stereoisomers. These are actually conformations. We have two conformations of ethane. They're conformations because they are interconvertible by free rotation. Rotation along that carbon-carbon bond can transform the first structure into the second. The second pair of models represents a pair of stereoisomers. They're not the same molecule, they're not superimposable upon one another, and they're not interconvertible by free rotation. The only way you can turn one molecule into the other is by breaking bonds, say by swapping out two groups attached to the carbon. The first type of stereoisomers we're going to look at are geometric isomers. Geometric isomers are just stereoisomers that arise due to a restriction in free rotation. These are commonly found in substituted ring systems and substituted alkenes. So here I've got a pair of substituted cyclopropanes. And you can see that the two green substituents in that first molecule, they're pointing in the same direction. They're both on the top side or top face of the plane of the cyclopropane. In the second structure, the two green substituents are pointing in opposite directions. They're on opposite faces of that three-membered ring. So they have different spatial arrangements, but the atoms are still connected in the same way. The only way you can interconvert those structures is by breaking bonds. There's a limited amount of free rotation in a small ring, so you can't just do a free rotation along that front carbon-carbon bond to interchange those two structures. The second pair of molecules represents geometric isomerism in alkenes. Again, you can see that they have the same formula and that they have the same connections, right? We have sort of a CH3, single bonded to a CH, that's then double bonded to a CH, and then single bonded to a CH3. But they have different spatial arrangements. On the first molecule, you can see those two methyl groups are kind of both pointing in the same direction, both downward. And on the second molecule, the two methyl groups are pointing kind of in opposite directions, one upward and one downward. And there's no way that those can be interconverted by simple free rotation. Remember, there's no free rotation in a double bond. If you try to rotate a double bond, it disrupts the overlap between the two p orbitals, and that costs energy. So there are two varieties of geometric isomerism: cis-trans isomers and EZ isomers. The terms cis and trans are used when you're comparing the spatial relationships between two substituents. Cis is used when the two groups are on the same side, and trans is used when the two groups are on opposite sides. So first here I've got those same disubstituted cyclopropanes. Because the two non-hydrogen substituents, those green substituents, are on the same side of the ring in that first structure, right? They're both pointing upward. That's the cis isomer of that particular disubstituted cyclopropane. In the second structure, the two green substituents are pointing in opposite directions. And since they're in opposite directions, that is the trans isomer. We can see the same thing in those two alkenes. In the first molecule, the two non-hydrogens, the two methyl groups, are both pointing in the same direction, downward. That means that's the cis isomer of that alkene. And in the second structure, the two methyl groups are pointing in opposite directions, one upward and one downward. So that's the trans isomer. Just remember that cis and trans, those terms, can only be applied on disubstituted rings and disubstituted alkenes. There's a more general way of describing the stereochemistry of alkenes specifically, and that uses the EZ convention. EZ is only used on alkenes, nothing else. In order to determine which isomer you have, the E or the Z isomer, we have to apply the Cahn-Ingold-Prelog rules. The general process is pretty straightforward. You simply prioritize the two groups attached to each carbon of the alkene based on the atomic numbers of the first atoms. So here I've got two stereoisomers of the same alkene. If we look at the left carbon in the left structure, look at the two atoms directly bonded to that left carbon. We have a bromine on top and a chlorine on the bottom. Now bromine has a higher atomic number than chlorine, so it gets the higher priority, 1, and chlorine gets the lower priority, 2. We then do the exact same thing to the two groups attached to the other carbon of the double bond. So if we look at the right carbon, the two atoms directly attached to the right carbon are a fluorine and a hydrogen. And fluorine has the higher atomic number, so it gets the higher priority 1, and the H gets the lower priority 2. In the second structure, well, we have the same groups, but they're in different positions. On the left carbon, we have the same bromine and chlorine on top and bottom, so the bromine again gets 1 and the chlorine gets 2. But on the right carbon, we can see that the hydrogen and the fluorine have swapped positions. So now the 1 group is actually on the bottom, the fluorine, and the 2 group is on the top, the hydrogen. Once those pairs of prioritizations have been done, you simply look and see where the higher priority groups are relative to one another. If the higher priority groups are on the same side of the double bond, then you have the Z isomer. Z is just an abbreviation for zusammen, which is German for together. If the higher priority groups are on opposite sides of the double bond, then you have the E isomer. E is short for entgegen, which is German for across from. So in those two examples we had above, you can see that in the left molecule, the higher priority groups, the bromine and the fluorine, the 1 priority groups, are on the same side. So that is the Z isomer. In the second structure, we can see that the higher priority groups, the bromine and the fluorine, the 1 groups, are on opposite sides, top and bottom, of that alkene. So it is the E isomer. And if you want a really cheesy way of remembering this, just think of saying zusammenseid. If you say it kind of like that in that sort of cheesy, generic Eastern European accent, you'll never forget that Z means on the same side. Where the EZ system gets a little more complicated is when you have the same element bonded twice to the same carbon, but as a part of 2 separate groups. So let's take a look at this example. On the left, look at the left carbon of that alkene. It's directly bonded to a carbon on the top and a hydrogen on the bottom. Well, carbon has the higher atomic number, so it gets the higher priority. Now on the right side, look at the right carbon in that alkene. Both of the atoms bonded to it directly are carbons, right? So we have carbon versus carbon. Of course, carbon has the same atomic number. So there's a tie, right? Carbon and carbon are the same element. So what we do in this case is we compare all of the atoms that are bonded directly to the atoms we are currently comparing. So in other words, look at the top carbon, that methyl group, that carbon of the methyl group. That's what we initially were comparing. So what is bonded to that carbon directly? Well, 3 hydrogens, right? So we list out those 3 hydrogens and we order them in order of atomic number. Well, it's all hydrogen, so it's all the same. We then do the exact same thing to the lower carbon, right? What is directly attached to that lower carbon? In this case, it's attached to 2 hydrogens and a carbon. So we again order those according to decreasing atomic number. So it would be carbon and then hydrogen and then hydrogen. From there, we just scan our 2 lists of elements and we look for the first difference in atomic number. And whichever one has the higher atomic number gets the higher priority. So you can see that the ethyl group that's on the bottom, 2 bonds removed from the carbon that we're trying to figure out the priorities on, we have a carbon and a hydrogen and a hydrogen. On the top, that methyl group, we have a hydrogen, and a hydrogen. So there's a difference in the very first element, right? Carbon versus hydrogen. And since carbon has a higher atomic number, that means that that bottom group gets the higher priority. The ethyl group has priority over the methyl group. And that means that the 1 priorities, the high priority groups, are on opposite sides, making this an E isomer. The last thing you've got to consider is how to treat other double and triple bonds, other multiple bonds. So let's take a look at this example here. We've got 2 double bonds. Now realize that only one of those double bonds, the one on the left, actually has stereochemistry. The alkene on the right part of that structure cannot have stereochemistry. If you think about it, look at the rightmost carbon of that molecule. It's attached to 2 hydrogens, right? And those hydrogens don't go on to anything else. And you can't prioritize hydrogen over hydrogen, right? They're the same element. So swapping those 2 groups out would not change the structure. But the leftmost alkene in that structure, yeah, that's going to have stereochemistry. So it's that we're actually looking at. So the left carbon of that alkene is pretty straightforward, right? The 2 elements directly bonded to that are hydrogen and bromine. So bromine is the clear winner. It gets the higher priority. Now look at the 2 elements directly bonded to the right carbon of that alkene. On top, we've got a carbon, and on bottom, we've got a carbon. So it's a tie, right? The same atomic number. So we do the exact same thing we did before. The only difference now is that that top carbon is double bonded to another carbon. And for that, we simply treat it as though it were single bonded to 2 separate carbons. So in other words, that top carbon, it's bonded to hydrogen and carbon again, right? Because it's a double bond to carbon. And then we order that so that we have it in decreasing order of atomic number. So 2 bonds removed from our alkene carbon, we have a carbon and a hydrogen. Looking at the lower group, that ethyl group, that carbon is bonded directly to a hydrogen, and a carbon. Again, we order those in decreasing order of atomic number. So that would be carbon, hydrogen, hydrogen. And when we look at those two sets of elements, we actually have to go to the second atom, right? The middle atom. And we see a difference. The first ones are actually carbons in both cases, but the second one is a carbon for the top group and a hydrogen for the bottom group. And that means that the top group gets the higher priority. And if we go back and look, we can see that the higher priority groups, again, are not on Z same side. They're on opposite sides. And that means we have the E isomer. So just remember, when you're dealing with geometric isomers, cis and trans is only applicable to di-substituted systems, either a di-substituted ring or a di-substituted alkene. The EZ system is only used on alkenes, and it must be used when you have more than two substituents to compare.